Welcome to our microlearning channel. In today's video, we will be discussing on edge computing, which is about processing data locally to reduce latency and bandwidth use. As the volume of global data explodes, the traditional model of sending every byte to a distant centralized cloud for processing has begun to show its architectural limits. Edge computing, the practice of processing data locally, near the source of its generation, rather than transmitting it to a centralized cloud, has emerged as a critical counterbalance. By performing computation at the edge of the network, such as on a device or local gateway, this paradigm dramatically reduces latency and bandwidth consumption. This essay explores the conceptual drivers behind edge computing, its core mechanisms, and its vital role in powering the next generation of real-time intelligent systems. Historical and conceptual context. The history of computing has oscillated between centralized and decentralized models. The early era of institutional mainframes gave way to personal computing, which was then largely supplanted by the centralized cloud model in the 2000s, where storage and compute were delivered as a utility over the Internet. However, the proliferation of the Internet of Things, IoT, billions of interconnected sensors in vehicles, factories, and homes, generated data streams too massive and time-sensitive for constant cloud round trips. The physical latency inherent in transmitting data across continents became unacceptable for applications requiring instantaneous response. Edge computing arose not to replace the cloud, but to complement it, pushing computational capability outward to local routers, gateways, and the devices themselves. Core concepts: latency, bandwidth, and local intelligence. Edge computing is defined by three primary operational advantages. Reduced latency. By processing data on local hardware, such as a factory microcontroller or a vehicle's onboard computer, decisions are made in milliseconds rather than the hundreds of milliseconds required for a cloud communication loop. This is vital for physical safety and real-time control. Bandwidth optimization. Instead of streaming raw, continuous feeds, like 4K video or high-frequency sensor telemetry, to the cloud, edge nodes filter, aggregate, and analyze data locally, transmitting only relevant insights or metadata. This conserves expensive network capacity. Resilience and privacy. Local processing allows systems to function even when wide-area network connectivity is intermittent or lost. Furthermore, keeping sensitive data, like medical diagnostics or private surveillance footage, on premises inherently enhances security and regulatory compliance. Modern context and applications. Edge computing is the silent enabler of latency-critical technologies. Autonomous vehicles rely on edge processing to interpret lidar and camera feeds instantly, avoiding collisions without waiting for a remote server. Smart cities use edge nodes to manage traffic signals and energy grids in real time. In industrial settings, Industry 4.0 leverages edge analytics to predict machine failure before it happens, minimizing downtime. Yet, significant challenges remain. Edge devices possess limited computational power compared to hyperscale cloud data centers, requiring highly efficient, lightweight algorithms, such as quantized neural networks. Additionally, managing, updating, and securing a vastly distributed fleet of edge nodes introduces complex orchestration and cybersecurity problems. In conclusion, edge computing represents a necessary evolution in our distributed digital architecture. By processing data locally near its source rather than sending it to a centralized cloud, it solves the twin problems of latency and bandwidth bottleneck that centralized models cannot address alone. As the physical world becomes increasingly instrumented and intelligent, the symbiotic relationship between edge and cloud will form the bedrock of responsive, efficient, and resilient global computing.